So, hi everyone, I think we can start already. So, I'm Roksolana, I work at Cyclone. Also, I'm one of the leaders of local Women Who Code community. And today we're going to talk about streaming data processing. So, I'm going to tell about the streaming data concept itself, about some use cases, as well as I give an introduction to streaming with Spark, and we'll talk about the main types of streaming. And we'll show some use case we had at Cyclone, as well as we'll talk about the future of Spark streaming. So many companies are trying to build their solutions based on the real-time data. And these solutions can be built in multiple fields. So it can be fintech, for example, for banking transactions. It can be self-driving cars for building some kind of alerting systems. It can be e-commerce for building real-time recommendation systems, and the Internet of Things for analyzing some signals, for building alerts and monitoring. And all of these spheres are united by the need to get the data in real time, to get the results as soon as possible. So the data stream itself is just a sequence of data units, and they can be this stream is generated by one or multiple sources. When we talk about the data processing, we usually mention two kinds of processing, which is batch streaming and stream processing. Batch processing and stream processing. So there are multiple differences between the two, but we cannot say that both of them are like rivals. They can be like coexisting, or they can we can build like independent systems with independent types of processing. So batch processing usually operates on large volumes of data, and that's why the processing time usually can be counted in hours or days. While in stream processing, we work with real-time data, so the amount of time needed to process this data can be measured like in seconds or milliseconds. And many frameworks or systems allow to combine both of the types of processing, and sometimes it's called the lambda architecture. So I already talked about the use cases for stream processing, but batch processing is widely used anyway. And as I said, it can be used without stream processing. For example, the monitoring systems, or for building some kind of reports, like daily, weekly, monthly reports. In these cases, we do not need to process the data in real time. Also, banking transactions, which take like days or hours. Sometimes when we transfer our money to the account, we get the value, like the amount, only after a few days, for example. Another important sphere is science. So a lot of scientific experiments gather some data over a period of time, and only after that, this kind of data is processed. That's why we need a batch processing for that. And the last one is the transporting system. So we just need to transfer a good for our goods. And for example, we do not need to know the exact location at specific time period for each thing we transferred, but we just need to have some kind of a log. So there are a lot of aspects when we choose a streaming data processing framework or when we build the system itself. First of all, it's performance. So we need to decide for ourselves, depending on the requirements for our product, depending on the needs, how fast we need to process the data. So it's all about latency and throughput of our system. The next one, I combined both scalability and reliability simply because they like codependent in a way that when we scale our system and more machines are in the cluster, for example, we need to think about our reliability strategies, how we work with faults in our systems, whether it's fault tolerant or not. The next one, which is very important, is tool or framework ecosystem. By that, I mean whether our existing streaming framework or streaming module works with some other sources like databases, files, support, as well as other frameworks, for example, messaging systems, and so on. It can be quite a crucial factor, especially if we have some kind of legacy system and we need to like build in our module, or if we build a system from scratch and we already have some kind of requirements according to which we need to define which framework would be chosen. The next one is messages delivery semantics. When we talk about messages delivery semantics, it's important to mention three messages delivery guarantees. The first one is at most ones, which is the weakest messages delivery guarantee. In this case, the message can be transferred or the data can be lost in the process of transferring or processing. These kind of message delivery guarantees are the easiest to implement simply because we do not need to check whether our data is transferred or not. The next one is at least once. In this case, we need to check whether our data was transferred, so there is some kind of fault tolerance mechanisms. But at the same time, there can be some kind of duplication. For example, faults would occur, and our system is like retries, and we process our data once more, or even twice. So this kind of system is a bit harder to implement, but it's probably one of the most popular ones for existing frameworks, as it's quite possible to implement this kind of guarantee. While exactly once is the strongest one and the hardest to implement, simply in a way that we not only need to think about faults that may occur in the system, but at the same time, we need to think about some data deduplication mechanisms. So when we look at these guarantees, we need to decide for our system whether we need exactly one guarantee or whether we can use some weaker guarantees, because it doesn't mean that we always need to build the strongest system in this way. So there are a lot of frameworks in the field of streaming data processing. A lot of them are open sourced, and all of them are depend on the requirements to the way we want to process our data. So there is no uniform solution to our streaming problem. And today we're going to talk about Spark, and specifically about streaming module. So why exactly about Spark? Simply because it's one of the most popular frameworks in the big data field, and it works quite well with multiple sinks and sources, so it has a very rich ecosystem. And another unique feature of Spark streaming specifically is that it can work with batch processing in one system quite easily. That's why it has become so popular. So it has a wide ecosystem, as I said, and today we're going to talk about Spark streaming module specifically. However, it works quite easily with other modules, for example, Spark SQL, MLlib, and so on. And all of them are based on the main Spark abstractions, which are inside of the Spark core or data frame API. Also, we have a data source API, so there are a lot of data storage systems, databases, file formats which are supported. In Spark streaming, we have two basic types of streaming data processing. It's basic streaming and structured. In basic streaming, which appeared the first, we operate with more unstructured or semi-structured data, so it's an RDD of some type. And in structured streaming, we work with data frames, so it's more like relational kind of structure. The main concept of Spark streaming is microbatching. So instead of simply processing the stream itself, we process each, not like data unit, but a couple of data units in a batch. And this batch is usually quite small. That's why it's called a microbatch. This is the reason Spark streaming is called a fake streaming, because we do not operate with each data unit. We operate with microbatches, so it's a batch processing in its way. Also, we launch usually some short tasks on each microbatch, and the stream itself is called a DStream if we work with basic kind of streaming. So as you can see, DStream is just a discretized stream. It's called in this way. And each microbatch is an RDD which contains some kind of type after each time interval. We can perform multiple transformations on the DStream. It can be mapping, flat mapping, but the main point is that after each operation, we get the microbatch in a stream. So the result, this stream consists of these microbatches, which are results of each operation. So you can see here that we have a lines DStream, and after flat map, we get words DStream. In structured streaming, it's a bit different, as we have structured data. So our stream is actually just an unbounded table. And each microbatch is not an RDD, but a new row, which is appended to this table. Also, we can perform a lot of transformations with structured streaming as well. So, for example, we can build some incremental queries. And the result table size, here I defined it as a uniform, and the same for each kind of output mode. However, it changes. when we define the output mode for our operations. For example, append is the output mode when we have some new data. For example, we map, we filter, and after each microbatch, new data arrives, and we process it, and the result table grows. In complete mode, we have to build some kind of aggregations. For example, we would count an average value for the whole stream. And we do not need to keep some kind of old data for the previous microbatches. That's why we just overwrite the whole result, so it's complete mode. Update is more like a combination of the two. We just append new rows if we need to, or at the same time, we can overwrite existing ones. Another important feature of streaming itself, not only Spark streaming, is window transformations. Not all the frameworks implement this kind of feature. Spark streaming has it. So window transformations are about running some kinds of building these maps or flat maps or aggregations in the window, not only microbatch. So visually, it looks like this for the DStream. We have some kind of original DStream of microbatches, and this time we do not get the result after each microbatch. We combine them in a window, like in a small batch in itself, but this window depends on the window size we define. For example, we can define, like here, the window size of 2, and we have 2 microbatches in a window. The next window starts from the third one, and so on. So the result can be any window-based operation. It can be aggregation, mapping, and we get the window DStream. So this kind of window is called a tumbling window, as all the data is not overlapping between these two windows. Although there is a concept of sliding window when we have an overlapping between the previous one and the next window. For example, here the window size is 3, and then the next window starts from the third microbatch. So the results would be like overlapping. And the same way we can see that we get the windowed-based operation result only after the window finishes, after the operation finishes on the window, not on each microbatch. Also, we can define this sliding interval as well as a window size. So here's 2 sliding interval. Let's look at the example of how window transformations can look in the data. For example, we have some data set of animals, and we will just perform simple aggregation, like counting how many dolphins, snakes, and cats we have. And for that, we will use structured streaming. I'll show you on this stream that you have, for example, a couple of time intervals. Let's make it 5 minutes, just for simplicity. And we have, after the first time interval finishes, we have 1 dolphin and 2 cats. That's quite understandable. The next one, we get another data. For example, this time the snakes appear. And on the third interval, we have changes as well. But as you can see, the result table grows over time. So we keep all the results for the previous windows. That's why it grows over time. But here is another important concept, which is the concept of late data. For example, our processing got too long for some kinds of data, and for some reason, this data appeared later. So on the third interval, we suddenly see changes in the first time interval result and the second time interval results. So there are more dolphins and more cats. So what can we do about this kind of late data? Usually it depends on the storage system we have, so we need to define for ourselves whether we actually need to keep this data at all, or how much data we would keep, so whether our storage system is enough for that. And this is when the concept of watermarking appears. So we define how long we are going to keep the data. For example, here is 5 minutes late. Data is OK. We decide for ourselves that it's OK in our system. That's why when the results for time interval, the second time interval appear later, like in the third time interval, it's fine for us. We just keep this data. While it didn't work out for the first time interval because it happened like 10 minutes before, so we decide that it's too late and we do not need to keep our data. This all depends on our system, and as I said, this watermark is very flexible, and we need to decide whether it's time intensive. Maybe we do not need to keep late data at all, and we just have to get this analytics instantly. Also, there are a couple of output operations. These are like mostly for debugging, so it's console, different file types. However, in larger and more like production level systems, we use different storage systems, various databases or messaging systems. It mostly depends on the architecture. In Spark, not only Spark streaming, we have these kinds of execution modes. So it's client mode and cluster mode. In client mode, we run our application simply on machine we have, like a laptop, and we just use the resources we have. In cluster mode, we use a couple of machines, and we define the master. It can be standalone, Yarn, Mesos, and Kubernetes. So let's dive into examples. I'll show a bit of code, how it looks like in basic Spark streaming and structured, and we will start from the basic Spark streaming. When we want to run our application, like to define the start, we should define the streaming context. It's like an entry point for the whole Spark streaming application. While for each simple Spark application, we have a Spark context. So we need to define it for streaming context as well. Also, we have a batch interval. It's not like some kind of magic number. We can define it experimentally or according to the requirements. Batch interval practically defines how much data can be fed into a microbatch. So for example, here it's like 3 seconds. We have a microbatch of 3 seconds, and we have 3 seconds of data. So after we define the streaming context, the batch interval, we can start building our system. For that, we need to define the data source. I've built all these examples for Twitter data source simply because I do not need to generate some streaming load. It's just like streaming in itself. Also, it's quite easy to see the structure. Like we have text, we have timestamps, users, and so on, various kinds of data types. And I just included the logic of reading the data from Twitter in Apache Kafka. It works as a producer for our data. So our Spark application simply consumes the data, and we can build all the transformations without going to the logic of reading all this data from Twitter and processing it and parsing it, I mean. So here I omitted all the parameters for Kafka I had, as they are not really relevant here. So I defined just this create direct stream from Kafka and define the streaming context. And we have here the type string simply because in Kafka we should have the type for key and the value. And the last line is the most important here. As this is where the exact reading and processing of data happens. So when we look at the types, we can see that we have a DStream, which consists of consumer records. As I said, when we read from Kafka, we have this key and value of type string and string. And when we use the map method, we go inside of this DStream. And then we can call the value method, which is getting the values from Kafka. And that's why, in the end, we just get the DStream of strings. Then we can perform multiple transformations. For example, simple filtering, we just call filter on our stream. So we have a DStream of strings as an input and DStream of strings as an output. But we have less data as a result simply because we filter it. So in this case, we just filter the tweets by the big data word. But there, we can also work with structured data. For example, we can work with data frames when we build basic streaming applications. But for that, we need to run this for each RDD block, this method, which allows us to get inside of the DStream and work with data frame and with RDD, which helps to build this data frame. So this is how it looks like. We have a DStream, then we run for each RDD method. After that, we can work with RDD of type string. Then Spark session allows us to build the data frame using this read and schema method. Schema I didn't provide it here, but I created the schema for the tweet structure, which is of struct type. And then we run the load method and we get the data frame. After that, we can build aggregations, transformations, all on the same data frame. For example, here I find the minimum and maximum value of followers by the specific tweet. However, pay attention that all of that should be built inside of the for each RDD block. So it has some performance concerns in a way that if you process a lot of data, if you write the data to some more complex sink, for example, database, there are a lot of these kind of situations that can appear. You can find them in the documentation, even like the most basic ones, as well as more complex, which are hard to debug. So when we've built all these simple transformations, we can run our application, but for that we need to call this start method, which actually runs Spark application. So everything we wrote before is more like a blueprint. It's nothing is going to happen if it will try to launch our application without this start method. And wait termination allows to run our application, then wait for some faults, or if we want to stop our application. And using these methods, we are ready to launch our application. This is for basic streaming, but structured streaming has a lot of features as well, and you will see how it looks like for data frames and more structured data. So when we read from Kafka, we just have like more the structure which looks easier because we just define options for Kafka, the format in which we read, and the read stream. We can, if we would like to read from some other sources, we would use not Kafka for format, but for example, a file or other things, and we just run this load method. But in the end, we do not get a DStream, we get a data frame. So it looks exactly the same as we would work with Spark SQL, for example, and we would work with simple data frames. So in this way, we can see that we can work with static and dynamic data frames in the same way if we have structured streaming. And we can run this simple select. Here, just again, extract the values from Kafka, and using data struct, define the structure of my data frame. So in types, it looks like this. We have a data frame as an input. We call select. We provide this string, and already in the middle of the process, we get the data frame, and then I define the structure, so all the types would be properly converted. We can as well run filters. So here we define the column. For example, all the tweets here are filtered by the English language. And this, again, looks exactly the same as for the static data frames. So we just get the data frame as an input, then we provide a column, and we get the data set of rows as we run contains. As we run a filter method, also the same for aggregations. As you can see, we just group the counts for each tweet. So we have a couple of languages, for example, English, Spanish, French, German, and we get just how many tweets are in this language. And each time the data gets updated, and we get more tweets, and we order by the way of like which language is the most popular by these counts. So again, we just run the group by. This relational group data set is just like internal type for Spark. And after we count and order, we get the data set of rows. So it's more like, if you're not familiar with Spark, the data set of rows is like in the middle between RDDs and data frames. So it's like more structured, but at the same time, it has less structure than data frames. Also, we can perform windowed aggregations. This is how it looks like for structured streaming. We just simply run the same group by and count, but in the middle of that, we need to provide this run to the window method. So if you would just follow the first and the last arrows, you would see that we just run group by, we provide some window. For now, we just submit what's inside of this method call, and provide a column. And we get, again, relational group data set internal method, then we run count, and we get data frame. But if you would look what happens inside, you would see that we need to provide this column of our data, which is of timestamp type, exactly timestamp, as well as the window size, which is 7 minutes, and the sliding interval, which is 3 minutes. But we may omit the sliding interval parameter if we do not need it. Also, if you want to watermark our data, this is just exactly the same as the previous code, except for the second line, where we run this watermark method. So the same again, we provide this timestamp. So our watermark is 3 minutes. As you remember, the window size is 7 minutes, so just the window size passes, then 3 minutes, and our data gets too late, for example. Then we get, again, the relational group data set internal method, and as we get the count, the result is a data frame. To launch a Spark structured streaming application, we have to run the same start and await termination methods. But as well as that, we need to define where we would write our data. So it can be it's defined by the format. It can be a console for debugging a file or some more complex thing. As well as we need to define the output mode. As I showed before, we have append, output, a complete, and update. And for each kind of transformation, we would have a different result. For example, we ran filtering before. It should be append output mode, because if you would define complete, you would get an error that this is not the right one for this kind of processing. For aggregations like grouping and window transformations that I showed before, we have to choose, for example, complete mode. And after that, we can launch our structured streaming application. But after we start running our application, we can look at the data, but it's not just simply about the results. We need to think whether we want to improve performance of our application, whether we probably want to change the batch interval, and there are a lot of tools for that. For example, we can do more complex monitoring and tuning using some visual VM, JProfiler, by just profiling our threads in the system. But at the same time, the simplest one to use is Spark UI. It helps to debug easily when we just build our application from scratch. You can find Spark UI simply in the log. You have this message bound Spark UI 2 and started at. And then when you go to this host and port, you get this nice view of the graphic view. You have a lot of tabs here, but we will concentrate more on the streaming one. In the streaming tab, you can see the active microbatches, the completed microbatches. Also, you can see the processing time for each microbatch, so you would see whether it coincides with your expectations, the scheduling delay for each microbatch, and also the total delay is the sum of scheduling delay and processing time. So if total delay more or less equal to the processing time, it means that you almost do not have delays in processing each microbatch. Also, you can see visually which microbatch in process right now, which succeeded or failed if it happens, and for what reason. In Spark UI itself, you can run you can see the optimizers, how it happens inside of the queries, and you can see simple statistics using these charts. So you have some kind of input rate. If it's more complex source, in our case it was Kafka. So in Kafka, I can define this amount of time we can wait to send our data, the size of the batch, and this is how the input rate would change. But in the files, we can, as well, if we build our own generator of streaming data, we can configure it and tweak a bit and see differences in the input rate. Schedule and delay chart is practically flat here, simply because we almost do not have a delay. Also, we have a processing time graph. We simply see how much time it's required to process our data, and we have a total delay. On this image, you can see that they are practically the same, which means we almost do not have delays. But I've monitored a bit different load. I've increased the batch size in Kafka, and the amount of time to wait to send it, I decreased it to 0. So as soon as we get the data, we just send it, and that's why we see there is a load, and there is a scheduling delay in the beginning because too much data got generated. But over time, if we would monitor our system, we could see that there are a lot of spikes on this graph. So, for example, it means that we might change our batch interval, or there is some kind of trouble with our processing. And the same, you can see that these graphs are almost the same, except for the beginning of the graph, where we had this load, and we can see that the total delay now is different in comparison to processing time. So let's talk about the use case we've built. It was an internal project. So we read the data from Neo4j. It's a graph database. And we built some kind of fake streaming in a way that we didn't have the real-time data. We just had some data set, and we sent this data to Kafka, which works as a producer here as well, and Spark streaming works as a consumer. So Spark module just consumes the data in real time. It processes the data, and then it addresses Neo4j again just to run some queries. In our case, it was a recommendation. So we wanted to run the query, graph database query, to get the results and some recommendations for the users, and then view these recommendations by sending them to Elasticsearch. And Elasticsearch allows to connect to Kibana directly, and we would see our graphs in real time, how our data looks like, and so on. As well, if we would talk about this delivery guarantees here, Spark streaming is considered to have exactly once delivery guarantee. But when we build, for example, this kind of system, it doesn't mean that the whole system would have such kind of guarantee. As Spark streaming, when they say that they have exactly once guarantee, they mean that it only happens inside of processing of Spark application, while we cannot guarantee the same for all the sinks and sources connected to it. So Kafka is also said to have exactly once guarantee, but only after 0.11 release, so it was quite recent. And as well as writing a message to Elasticsearch are also considered to have exactly once guarantee. So Spark streaming module evolves over time, and there are a lot of features which appear after each release. And the first one to look for is probably a continuous streaming. So in continuous streaming, instead of running a microbatching, we have a stream of data, and we process not a microbatch, but data unit. So it's more like a close to or even real streaming. And we run long-running tasks over a stream itself, not after each microbatch. The same way, we have a Spark driver which launches these tasks. So in the code, it would look like this. We have, for example, filtering. We use append output mode as we run filter here, some output format, and only to trigger the continuous streaming, we just have to run this trigger method and define the checkpoint interval, which is 1 second here. And this is when we have a continuous streaming. And on the console, we could see, for example, how fast the data arrives and how fast it's processed. But there are still a lot of problems with continuous processing. It's an experimental stage. And it doesn't work with aggregations. So for example, if you would try to experiment and try to define continuous streaming on window transformations or counts, you would get the error simply because it's not supported yet by continuous streaming. So the first probably feature to look for is stable continuous streaming. However, as it allows to process data much faster, the latency of structured streaming, like TOPS, is about 100 milliseconds, while for continuous streaming is about 10 milliseconds or less. So it would be much faster, but for now, also continuous streaming supports only at least once guarantee, while structured streaming is exactly once, as we know now. Another interesting feature is streaming with deep learning. It's already possible to build machine learning models on top of streaming data in Spark, but building deep learning models would look even more promising. And another important feature, in my opinion, is stable Kubernetes support, as Kubernetes is becoming more and more popular, and a lot of applications, specifically in big data, are built on top of it. That's why it's something to look for. Here's the main resources I totally recommend. The first two are good for starting out, but at the same time to reference if you need to. The next one is mostly about performance. And the last one is more advanced. It's like the description of all the streaming or Spark modules, but more like internal and advanced level. Also, here's my contacts. If you would like to write some questions or just follow me on Twitter and GitHub, you're welcome. And I've built a wrapper for the examples of this talk. So there are more examples. There is code for Kafka application for producing the data. There is a code for writing to Elasticsearch if you're interested about it. Also, I'm planning to build the Kubernetes support, so you could follow on that. And thank you for your attention.
Thank you for Thank you for your report. I'm beginner to Spark, but I have a little project using this. My question could be simple, but did you encounter situations when you need to read by one Spark streaming from several Kafka topics, and when you need data from one topic and another one, did you encounter this? And if yes, how did you tackle that?
Okay, thanks for the question. Probably the main two solutions you could build. First of all, you could just combine the streams in one if they have similar structure or the same structure. So we just join the streams itself, simply reading them from Kafka and process as one stream. But if you have completely different data, you just, for example, in structured streaming, you can read it into different data frames and join the data frames. So it's quite not that costly operation in structured streaming. So it helps to enrich the data if you want to combine all the data or just get some specific columns from the first one or the second one.
Hello, thanks a lot for the presentation. My question is about the checkpointing. For your example, when you are streaming from Neo4j, how did you manage to store the checkpoints? And are you using the default checkpointing of Spark, or you just implemented some custom way of storing the offsets?
Okay, thank you. We use the checkpointing of Spark mostly, and all the performance questions which arise to this situation were mostly handled by building the queries, optimizing the queries in Neo4j, for example, if it answers your question.
Yeah, hello, I'm new to Spark also, and want just to clarify a question regarding the examples you have showed to us. On the page, I believe 35 or 45, there was example regarding the data, maybe 44. Yeah, that's the correct side. So you told here that you just takes data regarding the English language, but from my experience with Java streams, so does it fit this code to show the data also for Bangalore language, for example, because it will be not only English, because I believe method contains will give us more data.
Okay, here as you can see the column is tweet user lang, so yeah, I just use the structure of tweet itself, and in the lang column there are a set of languages. When I defined, for example, Spanish or even Chinese, all the symbols were the same as in this language, so here I only got the data from English language. So it's mostly about the structure of input data that I had, but probably if you would filter the data without this kind of structure, you may have some difficulties with that.
So hi, thank you for your talk. I have a question about more performance. So what happens if we have an uneven load on our service, and then it takes much more time to process one mini batch? So what happens if, for example, this time exceeds the
the batch interval or the processing time intended, yeah.
And how can we fix that problem? For example, use load balancing or...
Yeah, okay, thank you for the question. So visually you would see that some data got late. For example, when we saw on Spark UI the active batches, you would see that one micro batch is still in process, while another one appear in the queue. It's quite visually, and you would see that they are late and they are not getting processed, and you are still stuck on this one. Also, it would appear on the graphs. And in this case, you would solve it by, for example, increasing batch interval if it's not the first priority to have this kind of batch interval, as well as work with performance of the application itself. So for that, you would probably need more complex debugging tools like profiling your application. Probably you would see, for example, that there is some processing in the, for example, you write to the database, you would see that some connection problems or the query itself problem you need to optimize. So you would find out on which stage exactly some kind of bottleneck happened. And this is when you would decide which kind of performance tuning you need to apply to that. So it totally depends on the situation.
Hi, thank you for your talk. I would like to ask, can you explain a bit more about the watermark? Is that based on the real-time timestamp, or is it based on the timestamp stored in the events?
I didn't say about the timestamps, which are like event time or processing time. There is a difference between that. Event time is the time when the data arrives, and we, for example, have the timestamp inside of our input data, so it's exactly the time the data gets into the system. While we might have the processing time where the data, it's like how much time it's needed to process this data, and they have difference, the event time and processing time. And in the watermarking, we need to work with event time, as we have to see like exactly when our data should appear, while the processing time would help us like event time is inside of our data. So in the example before, when we had the Twitter data and we had the timestamps for that, we could see that we are on this time interval, but our data appeared only like before, but for some reason it got late. So event time helps to see that the difference and when we want to watermark.
Okay, thank you.
Hi, Shad. Thanks for sharing your knowledge. How did you manage how did you manage these problems that arise from an almost uncontrollable pressure of input data, and with how did you manage problems that arise from uncontrollable back pressure of the input data and with window aggregation leads to unbound growth of window states and thus to I/O problems with underlying the file system like HDFS?
It again depends on the which stage of processing we want to optimize. If you would see the load from the source itself, as I understand your question, for example, in Kafka, you can manage it by tweaking the parameters like batch size. So you could see that, for example, it's too much data you sent, or there is also this linger message like parameter, which allows to see whether you should, as soon as you get all the data you need in batch size, whether you just send it directly to Spark or you wait for some time. For example, you can set a few seconds, you wait for some time, and then you send your data. That's why you like have some kind of time to process the previous data. So if it depends on the source, if it depends on the processing itself, like when you build an application and you see that it's too slow, and for example, HDFS or some other storage system can't like work with that, again, you need to look at which kind of operations you perform. It strictly like depends on the, for example, streaming type. In structured streaming with data frames, you could always like use explain function and see what happens inside exactly each operation in Spark, and see whether the plan of performance of all the like stages are like coincide with your how you imagine it should look like, or probably something got lost, for example, the physical plan chosen has not the best performance. It can happen like this, the same way. Okay.
I have one more question actually. You mentioned about Kubernetes support. Did you try the Spark operator?
Yeah, I did.
And was there any problems for you? Why you decided to do something on your own, or?
We are actually using Spark operator right now very actively, and I must say that it has some problems because we started to use it when it was alpha. So there were some errors in the operator itself, like you couldn't even launch the example set. Also, so after some time, we wrote some issues as well, and we saw how fast it changes. Like after a couple of months, it was already in beta. It was much better. But there are also problems with the kind of library you would use for that. For example, we used before the official Java client, but it's not the best one. It has a lot of problems as it's just for example, null pointers exception where it should be the data, like status of our object in Kubernetes, and so on. So we decided to switch for the Fabricate IO. As far as I remember, Red Hat library. We just starting out, so I think it should be better. So it's not only about the running the code, but also about the Spark operator, which I think it's going to get better as soon as it gets to production. So some issues, they appear over time. Yeah.
Yeah, thanks.
No more questions? Okay, thank you.
Thanks.